All right, part 2 of relays and contactors. We're going to continue on where we left off from last class. All right, so this slide here is just the following slide from where we left off, talking about brushing contacts, contacts that actually self-clean themselves. So another type of contact that they have is, now I always butcher the pronunciation of this, bifurcate. Bifurcate? Bifurcate? I don't know. Anyway, the meaning is to divide into branches. That's based on the Merriam-Webster dictionary. But a bifurcated has, you can see here, this is a contact here, and what they've pretty much done is they've divided it into 2 branches here, or you can have multiple different branches. And what this does is allows your current on these contacts to be divided into 2 paths, 3 paths, 4 paths, whatever it is, but that current rating for each path is going to be smaller than what the total current would be, and that's going to not cause as much arcing, right? It's going to have a lower resistance, which is going to create a longer life for that set of contacts. So here's another side view, right, of 2 contactors or relays, right? And here you can see the side view and the top view, right? Based on the amount of contacts here is one set of contacts, but they're split here, right? And this is based on Form C and Form X, which we have not talked about yet, so we'll just disregard that for right now and we'll get to it. All right, and then here we have 2 sets of contacts, so it'd be like a bridge contact here, 2 makes and 2 breaks, that'd be Form X. All right, so as it closes here, you'd have it's 2 contacts here, but there's 2 points to each contact, so it's going to split up that current and allow a lower resistance, lower current, and a longer lifespan for those contacts. So getting to the different types of forms, all right, and that's in your around page 11 now. The ION might have changed since I last did this PowerPoint, but it's going to be around page 11. All right, so the types of they're going to talk about is Form A, B, C, X, and Y. And now this is something you'll probably want to memorize. If you do flashcards, this is perfect for it, and I really suggest doing it because these are really easy quiz and exam questions they can ask you. For example, they can ask you, hey, what is a Form A? What type of contact arrangement is Form A? And that would be a single pole, so SP, single throw, ST, and then NO is normally open. Right, so single pole, single throw, normally open contacts. Form B, be single pole, single throw, normally closed contacts. Right, stated right there. Form C, right, and that's the one we just looked at right here. Form C, right, it's a single pole, double throw. Right, so here's a picture of a Form C contact arrangement. You got your common terminal, the pole. You got your normally open and normally closed side. So that's a single pole, one pole, and double throw. That pole can be in contact with either one of these terminals. But this one here, the picture we talked about was the bifurcated type. Again, I have no idea if I'm pronouncing that right or not. I should really look it up. Anyway, then you got Form X. So it's a single pole, single throw, right? Single pole, single throw, normally open. Right, and it's going to be a double make. Makes are when the contacts come together, and breaks are where the contacts are going to be separating. Right, so it says a double make, bridge contact, and then Form Y is a single pole, single throw, normally closed, double break type of contact. So that contact is like this. Form X would be like almost like a bridge contact here. Right, so when the armature is pushed down, these contacts are going to be come in contact with each other, right? So both of these contacts are going to be made, or make a make, right? And then when you open up those contacts, you're going to have 2 breaks. So that's what they're talking about, a double make and a double break, so bridge contacts. So yeah, try to memorize these Form A, B, C, X, and Y types of arrangements based on those contacts, because those are easy questions they can ask you. All right, now talking about contact materials. We talked a little bit about it last class, but the most common type of contact materials on contactors and relays are going to be either silver, copper, or cadmium plated, right? And now there's advantages and disadvantages to each one of these things, so you can kind of determine where would be a good place to use these, what type of contactor and what type of relay you'd want to use these on. So we'll look at silver first, right? So the uses for silver are for lower voltages and for lower current applications. Again, that's because silver has a higher resistance rating than, say, copper or cadmium, right? So we're going to have a higher resistance, which is going to create a little bit more heat at those contacts. You want a lower voltage and a lower current application for when you're using silver as your contacts. The thing about silver is it's self-cleaning. So remember way back in first year when we talked about the advantages and disadvantages of silver, right? It's kind of like aluminum, right? You get an oxidation happening, but when you have silver, when it brushes up against each other, right? It cleans off that contamination on the silver, so they deem it a self-cleaning contact, right? It says the faces can easily weld together, which is not a good thing. You don't want your contacts to weld together. They can't open up or close. So it cannot be used in high current applications, which we talked about at the start there. Then we got copper, all right? Copper, we have uses for higher voltages and higher current applications because, again, it's going to be a lower resistance rating. I apologize. When I talked about silver, I was thinking aluminum. Okay, silver has a good resistance rating along with copper there, so kind of just disregard what I said there, so I don't have to remake the video. Anyway, silver is great, but again, it's going to have a little bit higher resistance rating than copper would have. Okay, and that's why copper can be used for higher voltages and higher current ratings. The surface is harder, right? So silver can be a little softer, copper is a little harder. So it can be used with higher spring tension or spring pressure. So when those contacts come together, we talked about those springs. The spring contacts can be a little bit sturdier because those copper contacts can actually slam together harder, not damaging the contact material. Copper is prone to pitting, which is very true, and oxidation, right? So they cannot be used for frequent switching under load conditions, right? So what you can have there is, if you have a current traveling through these contacts and you open and close them often, you're going to create that carbon buildup based on the arcing and sparking going on. So they will start to pit, which is going to cause a higher resistance, okay, at that point, which is going to cause more heat, which we do not like, and oxidation happening at that copper, which again is going to cause more resistance. So you're not going to be using these copper for applications or relays or contactors where you're going to be switching it on and off at high frequency. All right, and cadmium plated, you can use for higher voltages, okay, high current applications, and frequencies, frequent switching under load conditions. So this is ideal, right? So if you're going to be switching it on and off many, many times, you want to use cadmium. Okay, it can withstand strong spring tension because it's very hard, has a longer contact life, and maintains constant contact resistance, right? So yeah, you can have those together, and it's going to pretty much maintain that resistance rating, so you're not going to have any variance there. Does not conduct as well as silver, right? So yes, it's harder. You can put higher currents through it. It's not going to pit and have the oxidation problems, but it's going to have the resistance rating be a little bit higher than what your silver is going to be. So again, you're going to have a little more heat build up there. So again, there's advantages and disadvantages of all the different types there. And you can see based on the advantages and disadvantages where you would want to and where you would not want to use these different types. So again, this chart right here is saying it's page 23. It will be around there somewhere. Have a look at this. Again, for cue cards, it'd be great to put this stuff down. It can be really easy, again, exam or quiz questions. All right, then we're going to talk about labeling and contact ratings. All right, so they're going to label your contact rating somewhere on the contactor or the relay. All right. So contactor ratings. All right. Well, another picture here is easier to see. Right. Size 1 will be based on the size of the actual contact diameters. Right. It's saying it can handle about 27 amps based on the contacts. Right. Then you have the different voltage and phase ratings here, horsepower ratings, based on that contactor, as you can see. And that is it for relays and contactors. So I really encourage you to read through that ILM maybe several times. There's tons of information you guys can jot down onto cue cards. All right. But I encourage you to read through that. If you have any questions, please let me know. I'm going to now go through kind of just a breakdown of the contactor and the different parts of it so you guys can see it. We're not going to obviously get into lab 1 because you're not in lab right now. So you're not going to partner up or put your safety glasses on right now, but there's a contactor and some overloads that you'll be using for some motor starters in lab here, but we're not going to be doing that. So here's lab 2, just for future. But anyway, I'm going to pause it right now. I'm going to jump back into, and we're going to continue on with the breakdown of the contactor. Here we go. So we've got the contactor teardown. All right, and obviously you're not going to be doing this because we're not in the lab also, but you would be using your safety glasses. Pretty much all you need is a flat blade screwdriver, a NEMA contactor from the bench, and a pen and a paper to label what is what. But you can just watch me do it. All right, so to start, basic contactor operation. We already know this. We got the armature. We got your coil. We got your contacts here. We got your contact springs, right? And then when the switch is closed here, you can see the armature is pulled in. The contacts are going to come into contact, and your load is going to be turning on, right? So basic operation. Jumping back, there's 2 different types of industrial control relays. One is the IEC, one is the NEMA. We're going to be using the NEMA type in classes. All right, so you can just disregard the IEC, but you still need to know what they are. All right, so here is the front of a contact that you'll be using in lab. All right, you can see all the ratings there, 230 or 460, 60 hertz, 600 volts max, right? You can see your terminals here, the terminal labels for what's around the corner here. Okay, you can see the same thing here, right? So the actual NEMA terminal numbers, when they're talking about them, you can see is you have 1, 2, and 3, and that's these contacts right here that they're referring to, right? So here is the contactor with that cover with the labels off now. And this here contains the guts, the armature, the contacts, and all that stuff. So it pulls right out of the base of that contactor where the terminals are. Right? So this is the coil here. You can see the terminals. The coil. All right. Then you have the inside of the contactor, and you have the armature spring, right, which is going to return the armature back to its original state as quickly as possible. You have your coil, right? Again, it's just another look at it from a different angle. That's your coil there, right, which your armature is going to go inside that hole there. Here is your core, right, which would be inside of that coil, and then your armature, which is going to be attached to that coil and to the core, right? With armatures, you can actually move there, so it's not attached, but it's going to be moving based on what this core is doing and then what that coil is doing. So here you can see the shading coils. You can't really see the laminations there, but this core would be laminated, right? And each pole here has a shading coil on it. And the purpose of that shading coil is to help reduce chatter. So when this core becomes magnetized, it's going to pull in the armature. But when that sine wave comes down to 0, it's not going to release because the shading coil is going to now have a magnetic field, which is attracting the armature and holding it in place until that sine wave increases again, and the core is now a stronger magnet, then you get to that 85% to hold in the armature. All right, well, there's a better picture there. Shading coils. All right, it's just a continuous loop at a 90-degree angle to your poles. And there's a better shot. You can see the core is laminated, right? And the purpose of that is, anybody? All right? To reduce eddy currents. So we laminate that all to reduce eddy currents, pretty much the heat buildup inside of my core. Because again, heat buildup is just your power, the energy in that circuit being lost into heat. So you have to pay for that, and those are all the losses you don't want to have to pay for. So that's your coil and your armature sitting inside of the coil. Right? You can see your core there, right? And the armature sits right in there. So when the coil becomes energized, the core is going to be magnified, turned to a magnet, and it's going to suck the armature in, and the shading coils, of course, will hold it in place. Just like so. And again, the armature is then going to be attached to your contacts, right? Oops, sorry, go back. That's the armature spring there, which is going to help it return back to original state when the coil becomes de-energized. There we have our contacts, right? Our stationary contacts and our contact springs here, right? And again, that's going to absorb the shock when those contacts come together very quickly, and it's going to what's the word? It's not going to allow it to bounce. You don't want that bounce to happen because it's going to create arcing, right? Which is going to create pitting or oxidation or carbon buildup on these contacts, which is going to create heat, which you do not want to have, right? So these absorb the blow from the contacts hitting, and then it's going to reduce all of that. All right, and there's your contacts in your relay or your contactor. All right. There's the stationary ones. Those are bridge contacts. Again, bridge contacts mean 2 makes and 2 breaks, right? And again, they brush. You can see the angle here, right? They're sitting at an angle, and they're going to brush so that they're going to self-clean. And that is it, I believe, for this lecture. There's a picture of a contact that's all pitted and burnt, and you have carbon buildup there, which is not something you want to have. Right? And then bifurcated, right? Again, divided into branches. We talked about that just earlier. And that's to avoid arcing and sparking by dividing up your path for your current to flow. It's going to lower the amount of current traveling down each one of these, which is going to lower the amount of arcing and carbon buildup. And it's going to have a longer life. We talked about the different forms, A, B, C, X, Y, which you'll probably want to chuck into a cue card, and the different types of contact elements you're going to be using for your contactors and your relays. So silver, copper, and cadmium plated. You see pictures of each one of them. The advantages and disadvantages of either one. And that, my friends, is all I have. So, again, please read through your ILM. If you have any questions, please message me, and I'll get right back to you. Thanks for watching.